Hello there and welcome to the series of videos going through the content of A-Level Maths. Here we're looking at differential equations in context and integrating them to find the answers so we can answer questions from exercise 11k. So we're going to be using the integration technique that we saw in the previous video, but we're going to be doing it now with wordy type questions. So in this question here, the rate of increase of a population P of microorganisms at time t in hours is given by this formula here. dp by dt is equal to 3 times p. That's effectively saying that the rate at which the microorganisms are growing by each hour is equal to tripling the microorganisms that are already in there. So effectively they're going to multiply by 4 each period of time that goes on. Each hour. Initially the population size was 8. Find a model for P in the form P equals A e to the power of 3t, stating the value of A. So let's take the formula that we are given and now apply the method of solving differential equations that we're given in the previous video. That is to move all the p's onto one side, all the t's onto the other side, making sure the p's and the dp's and the dt's are on the top. So times by dt, divide by 3p, or maybe just divide by p, leave the 3 on its own over there, and then start to do your integration. So we're now effectively integrating both sides of the formula here. The integral of 1 over p is ln p equal 3t plus c. So now we're going to inverse the logarithm by e'ing both sides. So now it's p equals e to the 3t plus c. And now somehow we need to create this a here. So this can be written as the product of 2e multiplied together. So it's e to the c times e to the 3t. Effectively what we're doing here is we're undoing that rule of multiplying the same indice will allow you to add the powers together. So now a can be used to represent e to the c, and that is a common strategy in these types of problems here, that we'll just use now a different constant number, and usually a capital letter as well, to represent e to the power of the c, where the c came from the constant of integration. Remember, because c is just a number, so therefore e to the power of c is just a number as well. So this is now what we're going to label as a. Now it says here the initial size of the population was 8, so when that means when t is equal to 0. When t equals 0, p equals 8. So substituting in those values there, and we get a equals 8. So therefore the formula looks like p equals 8 e to the 3t as our final formula. And then they usually give us a part B, C and D types to these questions here. So find to the nearest 100 the size of the population when t is equal to 2. So all that needs for you to do is just substitute in the value of t equals 2. So that would be 3,227.4. To the nearest 100, that would be 3,200. Part C is find the time at which the population is 100 times its starting value, so 1,000 times its starting value, or in other words 8,000. So P here is going to equal 8,000, and now we've just got to rearrange this formula here. So divide through by 8, get rid of the e's by lunning both sides, so ln of 1,000 equals 3t. Divide through by 3, and you should get 2.30, so about 2.3 hours, about bit less than 2 hours 20 minutes. 2 hours 18 minutes exactly. What you could do there is you could take away the 2, so subtract 2 and then divide by 60, and that will give you the exact amount of minutes that you need there. And the next question is state one limitation of this model for large values of t. Well, it's not possible for the population to grow exponentially forever, since it will eventually start to run out of food or space. Okay, so linking it back to the context of the question is really important there. Now that was quite a basic question there. Here is definitely a more harder type question. Water in a manufacturing plant is held in a large cylindrical tank of diameter 20 meters or radius 10 meters. Water flows out of the bottom of the tank through a tap at a rate proportional to the cube root of its volume. Now with that sentence there, we're definitely going to be making a formula, definitely a differential formula out of this sentence here. I'll have a look at that in a second. What's the question though? The question A is to show that after t minutes after the tap is opened, dH by dt is equal to minus k cube root h for some constant k. Now it definitely makes sense here that the height is going to need the rate of the height changing is going to need a negative symbol in there because the height is going to be decreasing. So the rate at which the height is increasing is a negative value. So what we're going to do now is we're going to think back to that differentiation chapter we worked on, the hard differentiation chapter, where we had to link different differentials together to get another differential. In this case here, what we're looking to get is dH by dt. Now what differentials could we use here? Well, we could use dV by dt. That's definitely what this sentence here is helping us to work out. The rate at which the water flows out of the tank is proportional to the cube root of the volume. That is definitely the rate at which the volume is changing. That's dV by dt. So we've got the dt on the bottom here. We just need now the dH on the top. Well, in that case, we need a dH on the top and then a dV on the bottom to cancel out the dVs there. Now the dV by the dH formula is probably going to be created by differentiating the formula for this cylinder. So let's get to it then. So dV by dt, we are told how the volume of water changes with respect to time. It's this thing that I've underlined in red here. And this dH by dV here, we can also create a formula linking the volume of the water to its height just by creating a formula for the volume of a cylinder. So let's get to these two components here. First of all, the first component here, we have the formula for a cylinder, which is V equals pi r squared h. That's effectively the area of a circle times by the height. And we know that the radius in this case is 10, so we can replace r with the value 10, so that's 100 pi h, and then we can now differentiate with this with respect to h, so it's now just dV by dH equals 100 pi. We're not looking for dV by dH though, we're looking for dH by dV, so it's all going to be 1 over 100 pi. Great, so we've got the second component here. We've got 1 over 100 pi. We're just now looking for this dV by dt term here. And that comes from the second sentence in our question here. Water flows out of the bottom of the tanker of a tap at a rate proportional to the cube root of the volume. So because it's proportional, we're going to need a k multiplier here. Now we've got a k multiplier in the question, so probably best not off using that k term there. Let's use a different term. Let's use something like c. Okay, so let's read what we've got here. So the rate of flow of water over time, that's dV by dt, the rate at which the volume is changing over time, is proportional to the cube root of the volume remaining. So the cube root of the volume, that's definitely going to be some sort of symbol to do with the cube root of V. This means that the rate of the flow can be written as minus, because the height is decreasing, c, because it's proportional to, and the cube root of V, because that's what it says the cube root of V, where c is the constant to be found, and V is the volume remaining. It is negative since the rate of flow is decreasing. So in this case here, dV by dt is equal to minus c times the cube root of V. Don't get this c confused with c being cubed. C is not being cubed here, it's just that V is being cube rooted here. So in this case here, let's get rid of that writing there. So in this case here, we're going to have dV by dt is equal to minus c cube root of pi r squared h. Where's pi r squared h come from? Well, that's the volume formula. Volume is equal to the area of the circle times by the height. So it's pi r squared times h is the volume for the cylinder. We know, however, that the r is 10 though, so we can substitute 10 in for the value of r. So in this case here, dv by dt is equal to minus c times the cube root of 100 pi h. And now all that's left for us to do here is just to times these two components together. So minus c cube root of 100 pi h times by 1 over 100 pi. Now unfortunately the 100 pi's don't just cancel out here because we have got the 100 pi inside a cube root symbol here, so don't just think that that can quite easily cancel out. And now separate the cube roots, so we're going to separate the 100 pi from the h inside this cube root here, so that we can now write this as grouping the terms together, grouping everything that doesn't involve the cube root of h here at the front here, times the cube root of h at the end. So now what we know is a value for this k term here. It's everything that is in front of the, behind the minus symbol and in front of the cube root of h symbol. So here k is equal to c times the cube root of 100 pi over 100 pi. Okay. So there we are, we have shown part A to be true. Now that is a really hard part of the question here. Now if you can't do that, then don't worry, because you've actually been given the formula to be able to now move on and do part B. So let's now go ahead and move on and do part B. Show that the general solution to this differential equation may be written as h equals, and in brackets, pi minus qt to the power of 3 over 2, where p and q are constants. So this is our differential equation here. We were shown that in part A. So if you haven't been able to do part A, you can definitely still have a crack at part B. And now we're going to use that technique of moving the h's onto one side, the t's onto the other side. And remember, k is just a number, so that doesn't really matter which side it ends up. So in this case here, we're going to times by dt and divide by the cube root of h. So now we're going to integrate both sides. Now in order to integrate this left hand side here, it would probably be better to write it as a power. And now we're going to use the integration rule of increasing the power by 1, dividing by that new power. So it's now h to the power of 2 over 3 divided by 2 over 3 equals minus kt. Now remember, k here is just a number. Think of it like minus 7. Minus 7 would integrate to minus 7t, minus k will integrate to minus kt, plus c. So what we'll do now is we'll times by 2/3 to get rid of that 2/3 on the bottom there. Don't really like that and how it looks on the bottom there. So we'll times it onto the other side. Now we've got to turn what we've got here into looking something like this. So the first thing I'm going to do is cube everything to get rid of the cube root on the bottom of my left hand side there. And then I'm going to square root everything to get rid of the 2 on the left hand side as well. So now this is going to turn into something very similar to what we want it to look like. H is equal to, and we'll just write it the right way round now, 2/3 c minus 2/3 kt, and in brackets all to the power of 3 over 2. So we can see here that obviously p is referring to 2/3 c, and q is referring to 2/3 k. Okay, so there we are. Part C now. Now we're probably going to have to be given some initial conditions to work out p and q. So let's see what we're given here. Initially, yeah, great. The height of the water is 27 meters. 10 minutes later, the height is 8 meters. And given that we've been given 2 conditions here, we can probably work out the value of 2 of the different variables. So going with the first condition then, initially that means when t is equal to 0, the height is 27. So 27 equals p to the power of 3 over 2. So square both sides, cube root both sides, and we get p is equal to 9. And then substituting in the other terms then, so t equals 10, and h is equal to 8. And we also know here that p is equal to 9. So simplify your algebra there, get rid of the cubing by cube rooting, get rid of the square roots by squaring, and we get q is equal to 0.5. So our model here can be written as h equals 9 minus 0.5t to the power of 3 over 2. And then the final part of this question is to find the time in minutes when the water is a depth of 1 meter. So when h is equal to 1 meter, let's find out the value of t. So undoing the cubing and the square rooting, we'll get just 1 still, because 1 cubed and 1 square rooted is just 1 still. Then we just need to rearrange to get t equal to 16. Okay, so there we are then. Quite a difficult question then. So your turn to have a go at this one here. Do take a while to do this. Don't just rush into it and give up because you can't do it straight away. Take some time over it and pause the video and try this one out. Okay, so let's get stuck into this question then. So a mug of tea with temperature T degrees Celsius is made and left to cool in a room with a temperature of 25 degrees Celsius. The rate at which the tea cools is proportional to the difference between the tea and the room. Show that this process can be described by the differential equation dt by dt equals minus k brackets t minus 25, explaining why k is a positive constant. So the rate at which the tea is changing is proportional to the difference between the tea and the room. Now I assume here that the tea has had to be boiled to a higher temperature than 25 degrees, so it's the difference between T and 25. Now it's left to cool, so evidently the temperature is decreasing by some proportion. So if I'm going to describe, show this process, so I'm going to have to describe what I've done here. I can't just write out the answer again. So this bit here is the difference between T and room temperature. The negative symbol here is because the T is cooling. And what does that mean? It means that the temperature is decreasing. And then why does K have to be positive? Well, because we want the whole temperature to be decreasing. Therefore, we've got the negative symbol. We now need the K term to be positive. So K is going to be positive because we want the whole change, or the differential, to be negative, and we already have the negative symbol. We already have the negative symbol. Okay, so there we are. That's answered part A then. Part B is to now work out the, find the temperature. So we're going to have to solve this differential equation, I imagine, at some point. So initially the T is at temperature 85 degrees Celsius. 10 minutes later the T is at 55 degrees Celsius. Find the temperature to 1 decimal place of the T after 15 minutes. So let's now go ahead and solve this differential equation. So we've got dt by d small t equals minus k bracket t minus 25. And now we're going to be using the technique of multiplying the dt onto the other side, dividing by this t minus 25 onto the other side, and then integrating. So equals, and we've got dt here, integral of minus k dt. So in this case here, we're going to have then ln t minus 25 equals minus kt plus c, because k is just a number. When it integrates to kt, and we've got plus c for the constant of integration. Then we're going to have t minus 25 equals e to the minus kt plus c. And then we're going to write ec as, we're going to write this whole term here as e to the kt times e to the c by splitting up the indices here. And we're going to write e to the c as the value a. So we're going to have t equals e to the minus kt times by a at the front, and then we're going to have plus 25 afterwards. So now we have an equation here that we can now start substituting values into. We know initially that the temperature was 85 degrees Celsius. So T, which is equal to 85 degrees Celsius, is when the time was equal to 0. So in this case here, we're going to have A times 1 plus C. So in this case here, A is going to equal 60. Where did this 1 come from? Well, it's e to the power of 0, so that's going to be 1. So it's going to be take away 25 from both sides, and we get A is equal to 60. Now we're going to use the other condition, and I hope that all this question is in minutes here. As much as left to go 25 minutes. Yeah, I have to assume it's in minutes then. So in this case here, we're going to have t equals 55 equals, now we know A, that's 60, and then it's going to be e to the minus k times 10 plus 25. So in this case we'll have 30 equals 60 e to the minus k times 10. Divide both sides by 60, we'll get a half. So it's going to be ln of a half equals minus kt. Now the minuses, if we think of this ln half as minus ln 2, the minuses will cancel. So we're going to, whoops, it's not 10, it's not t, it's 10. So in this case here we know that 10k is equal to ln 2. So k here is going to be equal to 1 over 10 ln 2. And I'm going to write that out as a value, but I am going to record it as well as that exact value for later questions. So that's going to be 0.0693. Now the final part of this question is to actually answer the question in part B. Then we've done so much work so far that we are now finally at the point where we can work out this value. Find the temperature after 15 minutes. So T here is going to equal 60 times by e to the minus, now in this case here we've got e to the minus kt, but we know that k is 1/10 ln 2. And then it's going to be times by t, so in this case here it's going to be 15 minutes. And then we're going to have plus c, which is 25 on the end. So the answer is going to be 46, once we've typed that all into our calculator. 46.2, we'll say degrees Celsius. Perfect, there we are. And does that make sense? Well, yeah, it's a little bit less than 55 and the temperature is cooling, so great, that makes complete sense there. So, thanks very much for watching this video. Have a go at plenty of the questions from exercise 11k, page 328. These are very tough questions, so don't be surprised if you do take quite a while at first to get used to them. Do go through all the questions, I think, in this exercise here. Do start with the more basic ones, build your confidence up, then move on to the problem solving and the exam style questions as well. Great, thanks very much for watching.